So the hardware-software interface was interesting because it was a computer science elective class that was in engineering. So it was the first and only engineering class I took. Right? And that went over some interesting stuff like finite state machine in the computing context, scheduling, utilization, and all that crap. Grand loops. I mean, I'm sure me talking about this rings a bell to you.
Yeah, sounds pretty standard.
Sounds pretty standard. And so our the learning stuff was pretty whatever, right? But the more interesting stuff was the projects we had to do. All right. So first off, in order to do the fucking projects, right? You had to spend $240 on an FPGA board. Right? So he advised the class to actually get into groups so that you can split the cost of the boards. This is an actual thing. Oh god.
Nice lag.
Yeah. So we had to buy the FPGA board, and it's like you should partner up so that you don't have to spend $256 by yourself. $248, my bad. $248 by yourself on a board that you're probably going to use once for this quarter and never again because it's an FPGA board. What's wrong with you, right? So, Jesus Christ.
Yeah, causing havoc in there.
Yep. There we go.
Security breach, they say.
Yeah. No, not really. No security breach in here.
No, there's no dead robots in here, officer. This isn't working very well.
No. There we go. Stop following me! Jesus Christ. This weapon feels worse than the unupgraded version. A little bit. Oh no, man. I'm not feeling it. So, 248. So I was like, damn, I'm not gonna spend $248 on a board that I don't know how to use. I'm gonna have to find a partner, right? And so like one day, so basically what happened is that one day before class started, there was just some guy just sitting in a desk, right, just waiting for class to start, and I'm like, hey, do you have a partner yet? I'm like, no, I'm actually worried about getting a partner myself, right? I'm like, are you in CS? Like, no, I'm in computer engineering. I'm like, oh, I guess we can work together then. So that's how I got my partner.
Nice.
More of the story, actually go out and talk to people. It'll work out. More likely than not, it'll work out. Nice shot. Nice death. Oh my god. Yeah, so talk to people. Talk to people. It'll work out in your favor a lot of the time. Oh, is he gonna die? There you go. Oh. Rip. Oh, he shot himself before I even hit him with the bomb. Of explodey gooey stuff. That sucks. So our projects are like, oh, use these attachments and write codes to do stuff with them. So our first lab with the board was making a timer like a stopwatch timer, right? So we had so on our board there's these seven segment LEDs, and we're supposed to press a button to make it start, and then press a button to make it stop, right?
Okay.
And so initializing the board to do all that crap is a whole bunch of pain and nonsense.
Did you have to send commands to a bunch of port registers or something?
No, we just used interrupts.
Oh.
We had to set up this interrupt controller, and then
That sounds a little bit worse.
oh no, I feel like this. I think we're just talking about the same thing, but in different context. Honestly, we might be talking about the same. We might be complaining about the same thing, but basically we had to. So in order to get the interrupts to work, right? You first have to find the device on the board, which is a variable, right? So you got to figure that out. You got to figure out the macro for that, right? Then you have to figure out where the interrupt controller is, right? Find the macro for that. Then you connect the device to the interrupt. No, you initialize the interrupt controller so that it actually sends interrupts, you know? Right? Then you connect the device to the interrupt controller so that the interrupt controller receives interrupts, knows to receive interrupts from the device, right? Then you have to enable the interrupts on the device so that it actually sends the interrupts. And then last but not least, you have to connect the device to a what's the word I'm looking for? To a function, to an interrupt handler, so that when the interrupt happens, it does something. Those are the steps you have to do in order to get interrupts working. You understand?
Seems somewhat similar to what I recall having to do.
Yeah. So then we're probably talking about the same thing.
Though there are also cases where I have to like set up the inputs, like figure out whether they're going to be tri-state or not.
Yeah, I had to do that in the interrupt handler. So basically, okay, you're in the interrupt handler now. Read the state of the board, right? And depending on what the state of the board is, do these commands. Sound familiar?
What board did you have to use?
Microblaze, or microblaze processor. Not exactly a.
That doesn't sound familiar for what I had to use the PIC 32 and probably the PIC 16. So pretty much we had to do a lot of stuff in assembly.
Yeah. Oh fuck!
Nice. Don't die.
Fuck!
I said don't die!
So we made the stopwatch, right? You press a button, it makes the thing go up. Also, by the way, the how 7-segment LEDs work is that only one can light up at a time.
Yep.
So if you have 8 7-segment LEDs, you can only have one of them activate. So you have to cycle through all of them over and over again.
You have to do some persistence of vision tricks.
Yep. So you have to cycle through them constantly, right? In order to get them to show up properly. Otherwise...
I had to do that in digital systems design.
Yep. You know it more than I do, because this is the first time I was working with it. Jesus Christ. Yeah.
I think what we had to use was Xilinx.
Xilinx, yeah, we use Xilinx.
What do you think about Xilinx?
It's alright as a... Let me try to remember correctly. Xilinx is the software development kit, right?
I think it is.
Okay, I was gonna be like, yeah, Xilinx was the processor that. Wait a minute, that's not correct.
This terminal should give.
And that wasn't correct. It's just the SDK. It's basically just the processor IDE if we want to talk about it generously. Right? Would you call it that?
Yeah, probably.
Yeah, we use C. We use C. No, just C for ours. Yeah.
Oh.
What did you have to write it in?
How do you work this camera?
DSD, I think we mainly had to use Verilog, because we were doing hardware stuff.
Yeah. So you didn't actually do any software. You just used logging stuff.
No, this is synthesizing hardware.
Oh, so it's not software at all.
No, this was fully hardware.
Okay, yeah.
But the concept's still the same for
Yeah.
like 7 seg.
Yeah, okay. I got you.
We had to do a similar thing, but in hardware, just not software.
Yeah. Ours was both, so yeah, I had fun with that. So basically, the arrangement we had for the two of us was that he was the CE guy, so he figures out how the board works, and I write all the code. And it was a lot of code, mind you, alright? Like figuring out,
Are you okay?
Sniper rifle! Oh, I shot the robot from across the... Nice.
Are you okay?
I'm alright.
Are you okay, Random?
They just wanted to give me the bad snoo, that was all.
You're supposed to be giving them the bad snoo, not them.
I'm alright. Can I turn them into a... Come back here. There we go.
Yes.
Oh, he died. There we go. Attack! He survived. Thankfully, he doesn't move. Alright, now kill the tank. Go! Go! Oh.
No.
Just face the... Can I bounce it off the wall? The answer is yes! You can bounce it off the wall, question mark. Murder them! Come on! Come on, fire pigeon, you can do this.
Fire pigeon.
What else would you call it? Ninja. The fire pigeon is actually super weak, what the fuck though? Alright, so I do all the coding, figure out where all the stuff is, enable them so that they work, and then have them do things. That's the software part. I'm great at that software. It's my major after all. And he basically just figured out how the board works and did testing.
How well did it work out?
It worked out pretty well. We did really well on the projects.
Nice.
Oh, he's dead. Hold up, he's dead. Oop, don't jump into fire. Oop. Don't, no! No! Fuck! Fucking goddamn. Okay. So first project was a stopwatch, which is fairly simple enough. Just cycle through all of them and update the time based on the count using the timer, right? Interrupts. The second one, if I remember correctly, let's see. The second one, I'm trying to remember the second one because I'm confusing it with the third one a bit. Hold up, I got this. Okay, the second one, we had to use a rotary dial. Do you know how those work? A rotary dial, basically a turning knob.
Oh.
Alright? Do you know how those work?
resistance.
No, I don't think so.
I'm probably thinking of one of those variable resistors then.
Yeah. But the basic idea is that you have the rotary dial has two inputs or two inputs, right? Two. It has two things it reads. A 1 and a 2. So there's two places that send interrupts, right? That send values to the interrupt, right? So basically, okay, I can't really explain this while playing video games. So basically, you have two positions in the rotary dial, right? Mm-hmm. And when you twist it, right, there's a on and an off thing inside the encoder, so that if it's not pressed down, it's a 0, and if it's pressed down, it's a 1. And when you're rotating, it rapidly like presses 1, and then presses both, and then releases 1, and then releases both.
So that's how it encodes the value?
That's how you receive values from the rotary dial.
Oh, neat.
So basically, if you're rotating it clockwise 1 tick, right? That's 0 0 and then 0 1 and then 1 1 and then 1 0 and then 0 0, and that's a 1 counterclockwise tick.
Okay.
And then if you want counterclockwise, it's 0 0 1 0 1 1 0 1 0 0, and that's 1 counterclockwise tick. So that sends 4 interrupts in a single tick. All right.
Oof.
Yeah. So we had to use the finite state machine to make it so that it doesn't bounce. All right, because the rotary dial is very susceptible to bouncing.
Oh yeah.
And I think you know a lot more about bouncing than I do.
It is terrible.
Alright, Mr. That Kid 4, explain to the audience what bouncing means and why it's a problem for everything in life.
So let's say you have a signal that goes on and off.
On and off signal.
So let's say you started it off and then you turn it on.
Yay!
What do you think's gonna happen? Do you think it just goes straight to on?
Yeah!
No, it doesn't! Fuck you!
Oh no!
It goes on and off and on and off before finally setting ring to on. No imagine reading that!
Yeah, so basically, what he's describing is a purely mechanical issue. Like, you'd expect it to just be off and then on, but because of how the off and on works, there's a interference in the workings of it, and it's not fun because of that.
And that's why debouncing exists.
Yeah, so we use the finite state machine to debounce the rotary dial, because otherwise it just goes back and forth between zeros and ones, and
it makes everything unusable.
Yes. So the finite state machine I used was just like a whole bunch of arrays. So like depending on he got fucking anti-aired by an explosive duck. So depending on your input, that's treated as a value between 0 and 3 inclusive, right? And depending on what state you're in, that value would direct to another state, or it doesn't, right? And if the transition has an output, then that output's a clockwise or counterclockwise, without reading multiple times. That was my solution, at least. And so that rotary dial, all it was supposed to do was, we have a row of 15 LED lights, and turning the rotary dial would just make it cycle through them.
Oh, okay.
That's all it was supposed to do. And then
he's got that 1,000 yards there.
After that project, we had to use an LCD screen.
Oh no.
Alright? And implement a volume bar. So have you heard of QP Nano?
What?
QP Nano?
That doesn't sound familiar.
Okay, basically it's basically finite state machines done easy.
You cheater.
Basically, the way QP Nano works is that you have signals that you send signals from whenever, right? And depending on those signals, it transitions to whatever state, right? And inside those states, you can code different types of transitions and methods and whatnot. Basically, just make it easier and not stupid and painful. So you initialize the signals, and then you make the signals, and then you make the states, and depending on what signals they receive, they do X or transition or whatnot, right? So we use that to make a volume bar on an LCD screen. Imagine my pain.
Sounds like pain.
Like we had to, depending on how you twist the rotary, right? It'll make the volume bar go up or it goes down, and if you press a button, it changes the output mode of the audio. Just on screen, it doesn't actually do anything. It just makes it say something different on screen. But not only that, so the real problem with this project, right, is actually the LCD screen.
Because drawing on an LCD is terrible.
Very, very terrible! Right? So, Mr. That Kid 4, how long does it take for a... What the fuck? That did no damage. There we go. How long does it take for an LCD, for a 240 by 320 LCD screen to draw one color the entire screen?
Longer than it should.
Good answer. It takes about
I don't remember the specific timing because it's been like a couple of years.
Yeah, no problem. For us using BRAM and not SRAM, or is it the other way around? Not using S. Okay, if we're using BRAM, which is the faster one for sure, right? Using the faster method, it takes at least a second or 2 seconds to draw the entire screen.
Oh jeez.
Yeah. And a second or 2 seconds is way too long to be redrawing the entire screen for, right? And this is only for a volume bar, right? And so we don't want to redraw the whole screen and then draw the volume bar on it. We want to just draw the volume bar and then erase just the volume bar by drawing the background over it. All right. By the way, our volume bar is also supposed to go away after 2 seconds of nothing happening. So we have to redraw the background over just the volume bar, and we had to make a background that was like squares. So it would be like your background is like a couple lines and a couple squares, right? So it's not a single color background, and you can't cheat like that, you bastard. So you have to figure out where your volume bar is, and then when you figure out where it is, redraw over the individual parts of the background over the volume bar. And then you're done with it.
Are you okay?
It was so... I had my function to redraw the background over the volume bar was like 200 lines of code. And I had to go into paint.net to actually draw the background that I made and then count which pixels were where and do it that way. And then draw it over and over and over and over and over again. But after all that effort, the end result was that we had a screen that drew over really fast. So that so that was easy and not stupid to use. So that was cool. We got an A on that one for sure.
Nice.
And then after that was our final project. I spoiled our project for you, so now I can finally talk about my final project. So this hardware software interface class. I meant to preface this, but I didn't get to it. But the class was actually a joint class between computer science majors and computer engineering majors, right? I mean, you should have implied that from my partner, right? And what the class is about, right? Like you can infer that much, right? The thing I neglected to mention though was that it was also a joint graduate and undergraduate class. So there was a whole bunch of undergraduates and a whole bunch of graduates in the same class, right? So because of that, there's a graduate and an undergraduate final project as well. So, do you know what the undergrads had to do?
What did they have to do?
They had to write a program that reads signals and put them through an FFT.
All right.
You understand those words that I'm saying, correct? If you don't, I'm gonna have to call into question your computer engineering degree.
Something Fourier transform.
Yeah.
Fast Fourier transform?
I believe it's fast Fourier transform. I take it from me, I don't know a jack shit about it, alright?
I haven't messed with it all that much.
Yeah, but you know what it's supposed to do, right?
It messes with signals.
Yeah, it's supposed to... Basically, the idea behind FFTs is that it's supposed to take in a signal, right? And then try to guess the frequencies of whatever signals there are in there. To elaborate, when you receive an input signal, it's not a single signal. It's a sum of a whole bunch of sine waves
that just happen to sum up to look like that signal.
Right. And so the FFT is supposed to be some easy way of easy way.
Decomposing it.
Yeah, decompose it to figure out how many signals there are and what their frequencies are and amplitudes, I guess. Time to suck. But their undergrad. Oh my god, they already died because the eggs are still on the field. The ducks are still on the field. So you need the. So they were just supposed to input a signal and then figure out what the signals are and shit like that. But the thing about the undergrad project is that they had the important code written for them. So they got off easy. The grad students, they had to implement a navigation device. Or let me put into context for this. My partner was a graduate student, so I had to do the graduate.
So you had to do the graduate.
Yeah, I had to do the graduate final project with him. All right. Let me tell you about navigation. All right. When I say navigation, what's the first thing that comes to your mind?
GPS.
Right?
This is a different kind of navigation.
All right. Does anything else come into your mind?
What definition of navigation are we using?
Just like figuring out where you are, based off of an origin position, let's say.
Maybe some gyro sensors.
Gyro sensors, all right.
You gotta figure out your orientation.
Right, orientation.
Would gyro also cover like height and such?
Gyro does not cover height, unfortunately.
So you'd have the gyro for orientation, you'd have GPS for general positioning.
Yeah.
What would cover height? Barometer?
Barometer? That's a good idea.
You had to do all of this, didn't you?
No, because we couldn't use GPS.
Oh.
Okay, so what kind of positioning system that isn't GPS can you come up with?
Not much. What did you have to do?
We had an accelerometer.
Oh no.
We had an accelerometer, a gyro, and a magnetometer, and a barometer, and we had to use these four. We had to use these four things in order to implement a full navigational system. How would you even begin? This is a grad project, all right? So that was the problem presented to me and my partner. We had to implement a navigation device which stores 8 waypoints that stores the relative position from a origin, right? So it would store a y coordinate from the origin, an x coordinate from the origin in meters, and height in meters. All right. So thankfully for us, the final project was in 2 parts. So the first part was getting a step counter to work. Do you know what I mean by step counter?
You take a step and it counts as 1?
Yeah, basically a pedometer. That's all it basically was. It was basically just a pedometer. But we had to implement that using only what we were given, which is an accelerometer. An accelerometer that measures acceleration in 3 directions. A gyroscope which measures orientation in 3 directions. A magnetometer which measures something in 3 directions, but we only use it for relative positioning from north. Basically just a compass, right? There's some math involved in there, but don't ask me what it's supposed to look like. Alright? It had something to do with ATAN, so you know what? I'm just not going to, get in there.
I love arctangent. It's my favorite trigonometric function.
Yeah. But basically, given an accelerometer, a gyro, a magnetometer, and a barometer, figure out how to calculate steps. So I'm gonna ask you, because you're not a graduate yet. How would you begin?
I guess the first step is trying to figure out what counts as a step.
Right. So how would you do that?
Okay, so what counts for the axes?
Axes are dependent on the unit actually. So.
Right.
So depending on how you orient your nav unit, the axes are positioned that way.
Because I could imagine it being based on at least 2 of the 3 axes.
Yeah.
Or like you have a base, and then you see if it goes up and then back down.
Yeah.
And then that could count as an easy step.
Yeah.
Like the only downside is it's probably very easy to game.
Yeah. Also, I'm forgetting to mention this, but I should mention this forever. That everything we do with all of these devices that we're given with have noise, which you assumed as a computer engineer, but no one else is going to assume that, right? If you don't have like backgrounds of these things, you'll never understand these concepts of noise and readings and shit like that, right? But you as a computer engineer, you know like everything there is to know about noise and how annoying it is to work with.
Yeah.
So not only is it noise, but it's also not completely accurate. So for example, the accelerometer measures acceleration in terms of G's. If you understand what I'm saying.
I'm not familiar with G's.
G's acceleration as a factor of gravity.
Okay.
So 1G is gravity, basically. So 1G is is 9 point whatever gravity is, right? So if you keep the navigation unit level, right, and with the z-axis pointing straight up and straight down,
Okay.
right, it reads gravity as 0.98 G's. So it's not entirely accurate.
Not quite it, Chief.
No, not quite it is right. So that's what we have to deal with.
Oh, great.
And then what was I gonna say? So we have to implement the step counter, right? And you say you don't really you have your own way of doing it.
It's probably not quite correct.
Yeah. So basically, what we did is that we took some data and like had it like print out on the screen, right? And then we took like the wavelengths of all three directions on the accelerometer and figured out which one looks most like a period, right? And we ended up having the navigation unit have X point straight in front of you,
Okay.
Y point to the side, and Z point straight up and down, right?
Okay.
And so we were actually given some why can't I access my... Oh, it's with this... okay, I got it. So we were given some articles to read about step counting, right? And so my partner said, okay, I read the article. They use something called zero crossing. So every time a signal goes from positive to zero and below, that's a step. Right? The problem is noise.
Yeah.
Noise. Even when you're standing still, right? The noise will make it so that it'll always go above and below zero constantly.
So there you go, set thresholds.
Yeah, so we have set thresholds, and even after setting thresholds, we still had phantom steps going on, right? So like it would still read steps even if we're standing still, which is what I mean by phantom steps. Right?
Yeah.
And then we're supposed to use steps to figure out how like the distance each step is for a navigation unit, right? Because that makes sense to do, right?
Yeah.
So our grade for the first part, our presentation for the first part was very wildly inaccurate with the steps and the distance because how would you calculate distance with an accelerometer? Let me put it this way. What do you use to measure distance?
Probably not an accelerometer.
You do not use acceleration to figure out where your position in a place is. All right. So the first thing, so you're saying, oh, we have acceleration, right? Oh, we can just integrate that twice to get our position, right? That makes sense, right?
Not necessarily.
In physics.
Oh, yeah.
In physics, right?
Yeah, in physics, but...
In physics, you integrate twice to get your position. So like you take the sum of all the accelerations in this time frame to get your velocities, and then you take the sum of the velocities in this time frame to get your position, right? Guess what fucks everything up?
The double integral.
No, I'll give you a hint. It starts with noise. Noise is the noise. If I learned anything from the computer engineering standpoint, it's that noise is your worst enemy in everything. So even if you're standing, if you walk like a couple meters, right, and stop, all of a sudden you're drifting forward at 50 meters a second.
Now you can finally do multi-track drifting like that one anime.
So we had to scrap. So we had to completely scrap the double integration.
Because you can't trust it.
Because you can't trust it at all. It's wildly inaccurate, and we had to, and so we ended up having to do heuristics. A heuristical analysis. So basically, our whatchamacallit, I don't want to do this anymore. Our project allowed it so that we can have calibration tests, so we can calibrate all of our devices to make it work properly as intended. Otherwise, it doesn't.
Funny how that works.
Yeah.
Sort of like the sensors I have for this thing. Like, I let it read it a couple times on boot, and then I use the average, and I set that as the 0 point.
Yeah. Also, how familiar are you with filters?
What kind of filters?
Just like signal filters.
Somewhat.
Somewhat, yeah. So
I know what a low pass and high pass and band pass filter is.
Yeah, all that crap, all that nonsense.
I know what those are.
Yeah. So, originally we were using an average filter, right? So basically, take a couple samples of a signal, right? Average them out, and then you get whatever, right? So we used the average filter, but because our step counter was reading phantom steps, my partner thought that the problem we were having was due to incorrect readings. So he decided to implement a Buttersworth filter. And since
know what a Buttersworth is.
And since there is confusion in your eyes, guess how much I know about it?
Absolutely nothing.
So he wanted to implement the Buttersworth filter, right? And so I went along with it. Like today, if you tell me what it's like, I can probably try to implement it, right? We tried to implement it. Guess what happened?
You got something that is not a Buttersworth filter.
I guess so, because our values ended up becoming very, very, very large in both directions. So it's like it starts off fine, right? Like you're getting a 1, -1, -1. I get or 0. Like 0.001, -0.001, and then it keeps going, and then it gets like 3.1 for wait a minute, -4.1, wait a second, 1066.
It's like that way where it starts off small and just gets bigger every time it goes up and down.
And like oh hey, that's an issue, and then it gets high enough that it actually crashes the goddamn thing.
Nice. Nice integer overflow, buddy.
Integer overflow? Buddy, we're using floats.
Nice float overflow, buddy.
Alright. I'm leaving out a whole bunch of... I'm going to talk about everything about this final project, and I realize I left out a whole bunch of stuff. I lost my multiplier. God damn it.
Yeah, because
I fell in lava.
You landed your butt on lava.
Alright, but our Buttersworth filter was definitely not working, so you know what? Scrap this idea. We're going back to average filtering, alright? By this point, we're already in part 2 of the final project. We already demoed part 1 with the step counter, and it wasn't working too well. But we had to present anyway, so like we had to show what we got. You know how that works.
Yeah.
But anyway, so we implemented the Butterworth filter, completely failed. So I had to come up with I came up with the idea of how to improve the step counter. Basically, when I was in part 1, when I was doing, well, for part 1 we ended up doing step zero crossing because that's all we had time for.
Yeah.
Because I did not have the schedule to work on projects for very long, because I was a very busy boy. Right? So when I was messing around with the data, I found out that when you took a step, it correlated to a negative acceleration in the up and down axis, right? So basically, when you're standing still, the z coordinate will read 1, right?
Mm-hmm.
But like when you step down, it would read less than 1. And the reason for that was because when you're stepping, right, the shock of your foot pressing against the ground actually sends a positive acceleration upwards, which counteracts gravity, right? So I found that, and I'm like, that's curious. That's curious, right? And then I said, okay. So I said, okay, this zero crossing. I said to my partner, this zero crossing isn't working, so I'm gonna try to implement a minima crossing, right? So basically, when given your inputs, right, read a local minima, and if you reach a local minima, right, that's a step, right? And so, and you don't refresh the step until it goes over, until you go over 1, as in like the normal gravity, right? So that was my information, and it worked so much better. It was to the point that the step counting was like 99% accurate after that implementation. It was insane. Like, holy crap, this is so accurate, right? And then we had heuristics to do. So now that we have an accurate step counter, we can actually fully implement a heuristic, like, properly. So like, if you walk X distance, we can calculate how many steps it took to reach that distance, and then every time we read a step, we just add that distance to your position, right? That makes it a lot easier, wouldn't you say?
Yeah.
How much of my explanation are you understanding right now? I just want to know.
I think I'm getting like most of it.
You're getting most of, like, if you were going to do this, you would know, like, you would understand, you would take from my explanation, right?
A little bit.
You're right. Okay, that's good. That means at least one person will know what I'm talking about. Too bad Quatron isn't here right now.
He'd probably just be super confused.
Yeah, I want to see that kind of face.
You want to see the look of pure confusion. That's what you want?
Who doesn't, right? Who doesn't?
Just watch me when I'm trying to figure out why stuff doesn't work in a rhythm game.
Rhythm game. Rhythm game. Where is this signal? I called it a signal. This is a fucking laser puzzle. It's not a signal. Alright. So...
What's in a signal?
Okay, so we have a step counter now, which means we could accurately do heuristics. And... So that was all well and done, right?
Mm-hmm.
So now that we have the... Oh god.
Whoa.
So now... Okay, so I'm gonna ask you a question now. We have an accurate step counter, which means we have a relatively accurate heuristic, right? Mm-hmm. So we know the length of a step now, and we can count the step, right? We also know the direction of a step in degrees, right? From the magnetometer, right? I'm gonna talk about the magnetometer later after this because that was a whole problem in itself, right? But you have the direction of the step, you have the length of a step, and you know it's accurate, right? How do you translate that into x and y coordinates?
Time for trigonometry.
Trigonometry, right? So you're probably thinking to yourself, oh, oh, my duck is still on the other planet. So you say trigonometry, correct?
Mm-hmm.
Right? So trigonometry, like, oh, you just use sine and cosine, right? And just add that to the x and y.
You probably need to do some arc sine and cosine, maybe.
No, you just use sine and cosine because like you have the length of the step, right? You just and if you want,
you can just in theory you could just use Pythagorean theorem, maybe.
Yeah, just use Pythagorean theorem. That's it.
But considering that you're the one who's telling the story, I can only assume it does not work like that.
So, as you may have guessed from me being me,
it didn't work.
So basically, sine and cosine, C math use it already has functions for sine and cosine, right?
It does.
And so, do you want to know what happened when we use sine and cosine?
Overflow? Crash? Explosion?
Not able to compile. You want to know why?
Does it need some features your system can't provide?
Something like that. You're getting there.
Does it return double?
No, I mean it does. The function returns floats, yes,
Okay.
but that's not the problem. I'm gonna keep having you guess because the answer will shock you.
Did you forget an include?
Nope.
Did you miss some pragmas?
Nope.
Did you define things dumb?
No. We did everything correct. The problem was that it took too much memory.
Oh. Oh no.
including C sine and cosine, what it had made the memory go over the amount that the board can handle by 2,000 bits. Because we were already using A10 for the magnetometer, so that took up a whole bunch of memory by itself.